Okay, a very good morning and heartiest greetings to all the participants. On behalf of the Department of Chemistry and the Internal Quality Assurance Cell of Maulana Azad College, Kolkata, I welcome all delegates to this one-day national webinar on Chemistry Alumni Lecture Series 1. We are organizing this lecture series not only to renew our bonds with the illustrious alumni of this college, but also hope that their achievements will serve as a beacon to guide and inspire the present batch of students in their future career prospects. With these few words, I now request the respected principal of our college, Professor Shubhashish Datta, to kindly deliver the inaugural address.
Good morning, everybody. My dear colleagues, beloved students, and other participants, I heartily welcome all of them to this webinar series. It's really a happy occasion for the college as well as the department that Department of Chemistry is going to organize a seminar, national level seminar, national level webinar, that too also as a part of Chemistry Alumni Lecture Series 1. Alumni Lecture Series 1. That means many more to come as the different distinguished, illustrious, bright, pass out students, alumni of this college will deliver lecture in the coming series. Uh, so it's a really happy occasion for the college, and I feel really proud for them. I personally congratulate the head of the department to organize such a such a webinar, and it is absolutely a kind of reunion with the ex students and with the present students, and deliver sharing the knowledge between them. So it's a really a very good occasion. I think this webinar will achieve its goal in full swing, and uh, I'm really privileged to inaugurate this webinar and wish a grand success. Thank you. Welcome, Professor Dr. Aslamanul Haq. I don't know in which year you have passed out, postdoctoral fellow of the University of Madison, US. I welcome you. I don't know that whether you are the student of this college when I was the principal here. I don't know. Anyway, I welcome. Thank you. Go ahead. Thank you all.
Good morning, everyone. Thank you very much for your kind introduction. So I am the batch of 2010 to 2030. So can I proceed?
Okay, if you would like to say a few words.
Yes, please, you go ahead. I can wait. Yeah, I'm sorry. Yeah.
Yes. Okay, thank you. Thank you very much, Principal Sir, for your inspiring words. I would now like to request the respected coordinator of IQAC, Professor Shubir Dasgupta, to kindly deliver his welcome address.
A very good morning to all of you. Respected Principal Maulana Azad College, Head of the Department of Chemistry, Professor Tapan Karfa, our illustrious alumni of this department, Dr. Muhammad Asamul Haq, Postdoctoral Fellow, University of Wisconsin, Madison, USA, all my fellow colleagues, and my dear students and participants. On behalf of IQAC, Maulana Azad College, I welcome all of you of today's webinar, which is delivered by one of our alumni of the chemistry department on the topic, the development of molecular catalyst for artificial photosynthesis and mediated electrochemical oxidation of organic compound. I hope that the present students of this department will be motivated and enriched from his speech. I wish all the best of today's program. Thank you.
Thank you so much, sir, for your inspiring words. I would now like to request the respected head of the Department of Chemistry, Professor Topun Kumar Karfa, to kindly deliver his welcome address.
Good morning, everybody. I am very much thankful to our Honorable Principal Sir for inaugurating today's webinar. I am also thankful to respected Professor Shubir Dasgupta, IQAC coordinator of our college, for his valuable speech. I welcome Dr. Asmaul Haq, ex-student of our department and speaker of today's webinar, organized by the Department of Chemistry, Maulana Azad College, in association with IQAC of this college. I welcome all the participants to this webinar. I hope today's webinar will open newer avenues for future introspection on the topic. I believe this webinar will be of immense knowledge in today's scenario. Thank you all.
Thank you very much, sir. After the inaugural session, we now move on to the technical session. I would now like to request Dr. Shubhadeep Shamanto, Assistant Professor of the Department of Chemistry, to present the introduction of the speaker.
So thank you very much, Professor Ajanta Mukherjee. Now, it's my immense pleasure to introduce to the speaker of Dr. Asmaul Haq, who is our ex-student. And here is present actually his old teachers. So he need not to be introduced too much from our end. Everybody knows Asmaul Haq and knows about his modesty, honesty, and also the academic capabilities. So Asmaul Haq was born in Antardip, a small village in Murshidabad, West Bengal, India, and he completed his undergraduate study from the Calcutta University with chemistry as a major in 2013. Then he moved to the Indian Institute of Technology, Mumbai, after qualifying IIT JAM entrance exam for his master's degree, where he was working with Professor G.K. Lahiri on designing and defining the sensitive electronic structural aspects of mononuclear and dinuclear ruthenium complexes, incorporating redox non-innocent ligand frameworks. After completing MSc in 2015, he moved to the Spain to conduct his doctoral studies at the Institute of Chemical Research of Catalonia, ICIQ, under the supervision of Professor Antoni Lobet. In the Lobet group, his research work was mainly focused on the development of the novel molecular water oxidation catalysts based on ruthenium and cobalt metals, their immobilization on the conductive surfaces, and benchmarking of their chemical electrocatalytic properties for water oxidation reaction. In the fall of 2018, Asmaul moved to the MIT for his 3-month research stay in the group of Professor Surendranath Jogesh, where he was acquired skills typical of electrode preparation with molecular catalyst and characterization in solid state for both oxygen and carbon dioxide reduction. So now presently Asmaul in Wisconsin to pursue his postdoctoral study under supervision of Professor Shannon S. Stoll at University of Wisconsin-Madison, USA, is currently working on electro-organic synthesis for both medicinal and as well as process chemistry. So, and about the Asmaul, as we have interacted with him, he let us know that in the spare time, Asmaul enjoy hiking, playing volleyball, badminton, and gardening. So he's a very jolly kind of chap, and we would welcome him to deliver his talk today. Thank you very much, all. With these few words, I would like Asmaul to carry on with his talk today. Thank you very much.
Good morning, everyone. Thank you very much, sir, for your kind introduction. Yeah, let me share my slide and then I will. Yeah, just a moment. Yeah, I'm good. Are you able to see my slide?
Yes.
Oh, yeah, thank you. Thank you very much. Yep. So good morning, everyone. And thank you very much, sir, for your kind introduction. So as sir mentioned that I am the alumni of this college, it is my great pleasure to present my work in this very nice platform. So the title of this talk, like as sir mentioned, that the development of molecular catalysts for artificial photosynthesis. So that was my PhD work. And then in my postdoc, I was doing this mediated electrochemical oxidation of organic compound. So before I go to the science, just sir mentioned briefly my background and introduction, but I want to just share my background by myself. So I born and brought up in Murshidabad district. So there is one small village called Antardippa. And then I moved to a city called Jangapur, and there my high school was in Guidance Academy. So I completed my higher secondary study in 2010. And then I moved to Maulana Azad College in Kolkata in 2010 for pursuing my undergrad study in chemistry as a major. So the guidance I got from that college helped me to build up my strong foundation in chemistry. And that was the reason that I crack and I qualify for the highly competitive entrance exam called IIT JAM. And after qualifying that entrance examination, so I moved from this Kolkata to Mumbai for pursuing my higher education, so master degree. And I got the admission in Indian Institute of Technology in Bombay. As you know, that this is one of the topmost research and the technological institute in India. So here I got this opportunity, and so when I came to this IIT Bombay, now I have a much more broad exposure in terms of, because I am mingling with the people from all over the India. So that helps me a lot to grow up and think widely and broadly in terms of all aspects, from the cultural aspect, from the scientific aspect, and in all. So in IIT Bombay, I joined this chemistry department. So during my master study, we need to do 1-year research project. And I joined in the group of Professor G.K. Lairi, and he's one of the very big scientists in inorganic chemistry in our country. And then there, I got the confidence also that working on the research field, and I got interest. So when I was in IIT Bombay, so that time when I almost completing my master, so I was having the two options. One is that I can get a job, because in IITs, you will have a very good campusing option. So you can get the job and then you can settle down. Or you have the opportunity that you can do even higher study. And that higher study you can do in India, or you can go abroad. So that time, with the help of friend and then discussion, I got motivated, and I thought, okay, why not to explore a bit more outside the India, and also in the purpose of doing the higher educations. So from India, and then I moved to European continents, a country called Spain. So yeah, this is the Spain. So I hope you all know that the Barcelona is a city of Spain, and that is very famous for the football. Okay. So the place I joined here is like 1 hour distance from Barcelona. So the city called Tarragona. So in that city, there was a research institute. So it's a pretty new research institute, and the name is ICIQ. So it is an Institute of Chemical Research of Catalonia. And in that, so that institute is pretty new. So it's established in 2004. But with the advanced technology and also with the very good human resource, this become one of the prominent institute in Europe for the research in in basic chemistry, I would say. So here basically it was only the chemical institute where organic, inorganic, and physical chemistry research were going on. So in that institute, I was working with Professor Anthony Lobert. So he was mainly focusing on doing the artificial photosynthesis. I'll come that one a bit later. So when I was doing my PhD study in Spain, we had like one program that you can go for 3 months research stay outside the country. So that time, okay, so before going that on, I just wanted to highlight that the city, the Tarragona city, so it is a very small city in Spain in that part, but it's really very beautiful. So in one side, you have this Mediterranean Sea, and you can see here these beaches. So that is very, very good place and relaxing place, because people and tourists are coming because of that one. And so as it was a very relaxing, so we are working the institute very hard. And then the weekend, we used to spend time here just by swimming or playing volleyball or playing many other activities. So if someone is not liking the sea or something, then he has the opportunity to go to the mountain area also, because the Tarragona city is situated in such a way that in one side you have this beach, or another side you are having the mountains. So you can choose any one of them. And here I'm showing one of the picture you can see. So that is called the Human Tower. So that is a very cultural and sentimental aspect of their culture. And that is specifically in this Tarragona city. Or basically, broadly, we can say this Catalonia province. So the significance of this culture, so they are celebrating that one in the summer. So the significance is that the goal is, it is the symbol of unity. So if we can work hard and all together, then we can reach as high as we can think of. So that is the symbol of their culture, of this occasion. And if you go a bit away from this Tarragona city, let's say 1 hour by bus, then you'll go to this Barcelona city. And here I'm saying this is the Barcelona Camp Nou, where this football, this is the famous, one of the best and famous football club all over the world, as you all know, and all are familiar with that one, I hope. So as I was just mentioning, so during my PhD, I thought to do a 3 months research stay, and then I decided to move a little bit further. So I thought why not to explore in US? So I applied that one, and I got the opportunity to work in MIT, so this Massachusetts Institute of Technology. And this is one of the best, I would say, the research institute and of the technological institute in the world. So once I was there, and then I realized that, okay, so it's given me a much more confidence and better confidence, and it helped me to believe that, okay, so if you can believe yourself, then, and if you want something, definitely you can get it if you are working on it. So so in that institute, I was working with Professor Suranath Yogesh. So he is an Indian American scientist. So he born in India, but he brought up and everything was in US. So he is an American now. And then I came back from MIT to Spain to complete my PhD. And in 2019, I completed my PhD. And then after that, I thought, okay, what next? So still I am having the opportunity to do the higher study. So I decided to move to do a postdoc. And for that, I moved again to the United States. And here I'm showing the map of United States. So you look in a broad way. So now you can see, so here is the Boston city where the MIT is situated. And for my postdoctoral study, I moved to a little bit of central. So it's a Madison city that belongs to this Wisconsin province. And And this is the university picture. It is a part of this picture because it's a very big public university in Wisconsin. So that is the biggest one. So in that university, this is the chemistry building. Even it has another building behind, and that is dedicated only for the research. So in that chemical, like in this chemistry lab, I was working with the Professor Shannon Stahl, and he's one of the leading scientists in the world in the chemistry. So here just I put my picture in for fun.
Sorry
So
to
yeah, I
interrupt
was
you.
working here.
Sir, your slides are not visible actually. Your slides
Oh,
are not
I'm sorry.
within the screen.
It is
Not
visible,
the,
Raju. It is visible.
Are you able to see?
You have some network problem.
yes, slides are visible over here.
Dr. Hawk, you can carry on.
Oh, okay. Thank you. Yeah, I was just a bit confused. Okay, thank you very much. Yeah. So here I am just showing the place, the city called Madison, where we are now. Yeah, and then university is situated. So I wanted to like show you the different mode of the Madison city. So let's say in the summer it is pretty, very beautiful, very greenery, and the weather is amazing. So if you move from this summer and then go a little bit of fall, then you can see aesthetic beauty of the nature, and then the leaves of the plants, they are changing their color, and it looks so beautiful and it's amazing. But unfortunately, this will not long last. It not long last for more than a month. And then the winter comes. So now you can see in this figure that whatever the blue color was here, that was the water, it's become completely white. So it's the nothing but the snow. And it stay like at least more than 2 to 3 months. And the average temperature sometimes in the winter, it can go to minus 30 degrees centigrade. And people are working at the temperature, not completely outside, but yeah, of course, inside. And like in the down, this figure I'm showing, so this is the picture just I took from the window from my home in the winter. And you can see this road is completely full of ice. So it's fun. It's amazing, it's wonderful experience, but also sometimes it can be painful because you need to go to work and you need to go through this very low temperature. But overall, I would say it's a very wonderful, like very nice place. Okay, so I gave you the brief background about myself. So let's talk about the science a bit. So I'll be talking in 4 different parts. So I have 5 actually. So I'll give first the brief introduction about my the research background, and then I'll talk the first half and the first portion is the homogeneous molecular ruthenium water oxidation catalyst, and then I'll move on to heterogeneous molecular oxidation catalyst, and then I'll talk about a bit of my postdoc work, that is mediated oxidation of organic compound, and then I'll conclude that one. So as we all know that the sun is the ultimate source of the renewable energy. So the current technology, what we have right now, is the solar energy technology, where we can capture the heat of the sunlight by solar thermal to convert them to heat, or we can utilize the light of the sun by the solar PV, and then we can convert the electricity. The main drawback in this case is that we will not be able to store this solar energy in this form. But the nature is very, very clever. So the nature is doing that things by natural photosynthesis. And it is doing that, it is capturing the energy of the sunlight and converting into this chemical bond of a compound. And then when you need this chemical, when you need the energy, you can burn that chemical bond. So what nature is doing is basically doing the oxidation of water molecule into a green plant, in the green plant inside the chlorophyll, generating this oxygen, and that is what we are inhaling. And then whatever the hydrogen is generating from this water is helping to reduce this carbon dioxide and forming this sugar and starch. And this sugar and starch ultimately turns to a fossil fuel. And also, this fossil fuel are currently now let's say all the technology is dependent on this fossil fuel. And also the many fine chemicals and our daily life is also fully dependent on this sugar and starch stuff. So due to the limitation, so we are losing fossil fuel day by day. So scientific community started thinking about that is there any way that we can get this alternation of fossil fuel? And yes, the thought came, and how we can do that, we can get the inspiration from natural photosynthesis and we can make it artificially. So is there any way that we can make it so that the purpose is that we'll absorb the light of the sun, and then the energy and light of the sun, and then we can store them into a solar fuel. And then whenever needed, we can use that solar fuel. So before going in that part, just I wanted to show you how this natural photosynthesis is working. So this natural photosynthesis is working in the green plant, as I said, in the chlorophyll pigment, and it has mainly three parts. One is called this photosystem 2, where the oxidation of water is happening to generate this molecular oxygen, and it generates these 4 electrons and 4 protons from 2 water molecules. And now we have this electron carrier, cytochrome B46, so that carries the electron, whatever is generating in photosystem 2, and transferring it to a photosystem 1. And now this photosystem 1 is taking that electron and also these 4 protons coming in the photosystem 2, combine them and reduce this carbon dioxide to a carbohydrate or sugar. And that is the source of all the energy source, whatever we are having. So inspired by nature, the scientific community tried to mimic that system. And they thought that we can design an artificial photosynthetic device, taking the concept from the nature. So what we can do, that we can have a device, and in one electrode called anode, we can do this oxidation of water to get this molecular oxygen. And then we can have this cathode material where whatever generated proton, we can reduce that one to a hydrogen by taking the electron from this anode side to a cathode. So that perfectly mimic the natural photosystem. So that is the photosystem 2, that is the electron carrier, and this cathode side is basically the photosystem 1. So that is one part. So if we can convert this proton to a hydrogen in the cathode. Another thing that I mentioned before, that we can utilize this proton source, whatever we are getting from this water oxidation, to reduce CO2 to this carbohydrate. Or we can do the reduction of very inert molecule, that is nitrogen, to ammonia, and that is very demanding because that is used for the agricultural purpose. And already Haber-Bosch got Nobel Prize for synthesizing those ammonia, but the condition was high temperature and high pressure. But we wanted to do with this artificial photosynthetic device that will be at room temperature with normal pressure, 1 atmosphere pressure and everything. So that was the dream. But whatever, so you can see that in all these three system, what I'm showing, that the main counter reaction is the oxidation of water to molecular oxygen. So that is why scientific communities try to develop a good or better molecular catalyst in order to carry out those transformation. So before going that development, I just wanted to show you this thermodynamic and all these parameters. So for example, the oxidation of water to a molecular oxygen is thermodynamically very uphill. As you can see that it has a delta G value, which is much more positive. So the breaking of this 4OH bond of a water molecule to generate one molecule of oxygen is energetically very uphill. So it has a very high activation barrier. But is there any way to reduce this activation barrier? Yes, there is. So if you can use this catalyst, then you can lower down this activation barrier and make this process facile. And nature is very clever. Nature is having this catalyst called this manganese calcium clusters, where all of this oxygen atom of this cluster is connected with the metal, and 4 water molecule in the periphery is completing the coordination pair of this catalyst. And it has an activity or turnover frequency in between 300 to 400 per second. So people got inspiration from that nature, that okay, so nature is also having this catalyst. So can we design some kind of artificial catalyst that can mimic this transformation? So yes, So people try to design this artificial water oxidation catalyst. So the first example of water oxidation catalyst came in 1902. That was based on the nickel oxide. So that is the heterogeneous catalyst I'm talking here. And then after that, there has been a tremendous improvement happening in terms of this water oxidation property. But one of the point is that the activity. So we want to have a catalyst, and that should show the catalytic activity, and how we can define that, which is one is good or bad. So the activity we define in scientific term is called the turnover frequency. So it is defined as that so let's say how many molecules of, let's say, water is getting oxidized to give the oxygen by using one molecule of catalyst in 1 second. So the top I'll be using throughout my talk is to benchmark the activity. So higher the top, or it means that higher is the activity. But in case of this metal oxide catalyst, so we really don't know which one is the real active side to improve their catalytic performance. So it has the main drawback that it's poorly defined active side, and we cannot improve the turnover frequency of the system. And then it came to develop this coordination chemistry. So after getting the Nobel Prize, this coordination chemistry became a topic of research. And the first molecular water oxidation catalyst has been discovered in 1982 by T.J. Mayer. So that is called this ruthenium blue dimer. So now you have a molecule which is well defined. You know that exact structure and structural relationship of all that molecule. And now there is a way that we can improve the activity of this system, because now we know what exactly. So after discovering this first molecular water oxidation catalyst in 1982, there has been a tremendous improvement over this past 30 years. And in 2012, scientists discovered a molecule, this molecule like 12, and now it has this activity, this turnover frequency, slightly higher than the natural photosystem to what it is working. So now we have this, like, let's say the molecular catalyst, which has the activities is close to this natural system, which you will never be able to achieve with this heterogeneous catalyst, this metal oxide based heterogeneous catalyst. But the development did not stop. So in 2015, our group, like the Lobet group, so they discover another ruthenium molecular catalyst, which is having the activity 1 or 2 order of magnitude higher than the natural photosystem too. So this is the current state of art of this development of molecular catalyst. And this development has been achieved because, as I mentioned, because of the discovery of this coordination chemistry. So let's say here is the metal center I'm showing M, and then L is showing this ligand center. So the judicious choice of the ligand around this metal center can control the geometry, oxidation state, static environment, and many other factors. So in particular, if we can think of for the water oxidations, there are some features that we need to consider. One is that one of the ligand must have to have the water molecule connection. And once we have this water molecule connected, so this metal aqua complex, we can oxidize by removing the electrons and protons, then we can achieve this high valent metal oxo. So once we have this high valent metal oxo, so that is very electrophilic in nature, and then water will do this nucleophilic attack onto this electrophilic metal center, and then will form this oxygen-oxygen bond. And then once we have this oxygen-oxygen bond, it can liberate and generate this oxygen gas or oxygen molecule. So we want a system. So like people got the information about the mechanism. So now we want a catalyst to design in order to make this process as fast as possible, and also making the liberating of oxygen molecule as fast as possible. And how we can do that one. So the main important parameter is the coordination environment. So how you are designing your molecule and what kind of ligand you are putting inside this molecule, that will play a lot. And that is the major role. But there is also another effect called the secondary coordination sphere effect. So where this effect is not directly connected to this metal center directly, but it can do some other activity with the secondary sphere, not into the main coordination sphere. So yeah, that was like basically the molecular water oxidation catalyst. But people wanted to think of designing the artificial photosynthetic device, right? Because we want to have a device that can do this transformation. So this is, I'm showing a schematic diagram of water splitting device. So where there will be an anode where we wanted to do this water oxidation, and with the expectation that we want to design a water splitting device, and then demand is that we should have the current density value is above 10 milliamp per centimeter square. And how we can do that one? So one of the option is that, okay, as I showed, this molecule is so far the fastest catalyst and the best catalyst reported in that in the literature. So we thought like, okay, so our group thought, then why not to put this molecule onto the surface? But how we are going to put? So we need this linkage. So we need to develop a linkage where this molecular catalyst can be anchored onto the surface. So the reason why we wanted to anchor, because we wanted to design a device. So when we'll be working the device, then we need to put our catalyst into a solid surface. If we are doing that one in the homogeneous, then it is not economically feasible. So to design this linkage, there have been a tremendous research also going on in that field. So I am giving a bit of summary. So the linkage could be a covalent linkage. So for example, like if you have an electrode surface that is made of metal oxide, so most of this electrode material, titanium, FTO, I2 are made of this metal oxide. And you can design your molecule in such a way that it can have a pendant carboxylate group, so that can react with this metal oxide and form this covalent bond. Or if you think of using this carbon-based electrode materials, then there is also option that you can form this carbon-carbon bond with this electrode through this covalent bond. Or another thing, what you can do, that you can modify the electrode surface, generating this dioxo group, and you are modifying your molecular catalyst. So imagine this R group is the catalyst, the big catalyst that I was showing, and that is somehow we functionalize with this diamine. And now this can do this condensation reaction and form this kind of the covalent bond. So with this system, what we are getting, that we are like making this molecular catalyst onto the solid surface. So basically we are generating this heterogeneous catalyst with knowing the molecular integrity of the catalyst. So this work, I have been working at MIT. I'm not going to show the detailed result about this one, but that group is very prominent for making this kind of linkage for doing artificial photosynthesis. But apart from this covalent bond, you can make this non-covalent interaction. So for example, if you are having this, let's say the carbon material, carbon nanotube that has a pi system, and you are defining and designing your molecule in such a way that it also can have this pi system. So now this pi-pi interaction can happen, and then it will form a strong connection and it can be stabilized. Another kind of, but very rare interaction is CH-pi interaction. So each of the organic molecule or any molecular system has a CH bond. So this CH bond can have this interaction with the pi system of the benzene or any aromatic ring, and then form the CH-pi interaction. So this is not exactly the covalent bond, but it is the stronger. But yeah, in that way, you can anchor the molecular catalyst. So that is still like the DFT calculation data is showing, but there are no experimental data to support that one. And also in other way that you can also design this molecular heterogeneous catalyst in such a way that you can think of designing the coordination polymer. So for example, let's say you have this well-defined molecular unit that is one single unit, and you can design the linker in such a way that you can make a polynuclear species. So still it is a molecular integration, but you are making this heterogeneous at some point. Or you can put this molecular catalyst into a well-defined system, the polymer, for example, this metal organic framework, and then you are basically incorporating the molecular catalyst into the system. So the reason why I'm highlighting this molecular catalyst, because now you have seen that I have shown you that with the molecular catalyst, you can have very, very high activity, the turnover frequency, as compared to this heterogeneous metal oxide based catalyst. So the goal, so that was my introduction. And then the goal of this, my project was to design this homogeneous molecular auto oxidation catalyst in order to reduce the overpotential. I will come into the next slide. What this overpotential is basically like you need to apply the minimum energy to get the maximum output. And then the kinetics, that we want to design a catalyst that can work as fast as possible. And then I defined like, I'll be saying, so then we thought like, okay, designing this heterogeneous molecular catalyst with the purpose of having this current density, because as I mentioned that we need a device which can have this current density above 10 milliamp per centimeter square. But this is not only the sufficient one, but it needs to have the stability. So we want to design this molecular anode that can work forever. That is what ideally we want. So that stability is basically the turnover number, is means like how many molecules of let's say the water is getting oxidized to a molecule over the time. So we will not care about the times when we are calculating the tone, let's say. So with that, so here I will move this homogeneous molecular auto oxidation catalyst. So here first I want to introduce the term of overpotential and kinetics, because that will be the main, let's say that the concept what I wanted to introduce. So imagine that the oxidation of water to molecular oxygen and hydrogen, we can, so it is energetically very uphill process, and that energy we can reflect in terms of the potential. So this potential value is 1.23 volt. And here I'm showing that is called the cyclic voltammogram. So the cyclic voltammogram is a technique where you are measuring the current by changing the potential of the system. So imagine that here, so this E0 value is showing the thermodynamic potential for doing this water oxidation. So that value is 1.23 volt. So to do this one, you need minimum amount of this much potential to carry out this one. But let's say you have a catalyst and that is showing this activity. So you can see when there is an enhancement of the current, that is giving the indication that you are doing this oxidation. So here, let's say you are doing this water oxidation. So the real applied potential is now here. So the difference between this thermodynamic potential and then the applied potential is called the overpotential. So then imagine that if we want to think of designing a molecular catalyst, if the overpotential is low, then we can say that that catalyst is good and then best. So our goal is to design a molecular catalyst which can have as low overpotential as possible. And the second is the kinetics, that is turnover frequency. So that is also, we can have this information from the cyclic voltammogram. This is, so for example, this black one is showing this current which is relatively low, and then the red one is showing the current which is relatively high. And imagine that those are under identical conditions. So which one is giving the higher current is doing this faster reaction. It means that that is giving the higher turnover frequency. So like with that purpose, first I like designed these 4 molecules, so ruthenium-based molecule. And as I mentioned in the introduction, that we need to have a water molecule connection into this metal. So we have this ruthenium metal, and one of the ligand is water. And in 4 compounds, I have this terpyridine common ligand, but we have the bidentate ligand, this quinoline, which is forming the 6-member ring around this metal center here. And we have this picoline, which is forming this 5-member ring around this metal center. But apart from that, everything's are the same. But if you look at like with this ligand, it shows 2 isomers. One is called trans, so where this carboxylate group is in trans position with respect to water. And in case of the cis isomer, this carboxylate group is in cis position with respect to water molecule. So now we have like 2 different kind of geometric isomer, and we have 2 different kind of ring size. And then we wanted to see that which one is working better and how. So again, I'm saying this one is the cyclic voltammetry. So that is a very good analytical technique and assay to define the catalytic activity, the turnover frequency, and then over potential, and many, many other things. So here, these are the redox spots. So this is related. So for example, here we are having ruthenium-2, and we are removing one electron from ruthenium-2 and then generating ruthenium-3. And as we are removing the electron, it's giving this current response, and that is why it is giving the bump. And with this bump, we are deciding the redox potential of that system. And in case of this, for water oxidation, as I mentioned, that we need the high valent metal oxide species in order to do this nucleophilic attack of water molecule. And this high valent situation is this ruthenium-4,5 oxo complex. So here you see that the black line is basically the trans isomer, and then the red is the cis isomer. So we have the, let's say the structural environment is exactly the same, but the relative dispositions of this carboxylate molecule changing the over potential. So for example, the trans one is showing approx 100 millivolt lower over potential as compared to the cis isomer. So you can see that by changing this geometry, just you can like the geometric position, you can lower the over potential. And then like, yeah, we calculate also the turnover frequency because we wanted to know which one is which one is working faster. And then we found that like here, this potential is basically, let's say, at the high valent ruthenium 4,5 redox couple. So higher is this, let's say, and this also can give you the idea of the over potential. So higher is the over potential, better is the activity. And that is what the Marcos theory supports, that one. So, and that is what we got exactly into the system. So now, like, we got that system, and then so basically what I'm showing here is that geometry can control both the redox property and catalysis. But in terms of over potential, if we think that we have, like in this molecule, one sigma donating ligand that is called this carboxylate, and has this over potential approximately between 0.5 to 0.6 volts. So now, like, this is the absolute over potential I'm saying. And then, yeah, this compound has already been reported where you have this neutral bipyridine ligand, and it has this over potential of approximately like 0.754. Then the question was, can we reduce this over potential even below to that? And we thought, okay, why not to try? And then I tried by considering in mind that we can change from one of the sigma donating ligand with two sigma donating ligand, like sigma donating anionic ligand, that is carboxylate. So we choose this pyridine dicarboxylate ligand and then bipyridine. So I have synthesized that one. So the goal was to get this ruthenium-3 aqua compound, but we found that this is a very unstable compound and forming this oxo-bridge dinuclear compound. But nevertheless, we can reduce this molecule electrochemically, and then we can isolate this ruthenium-2 aqua compound. So you can see that this unstable compound was an ruthenium-3 oxidation state, and that was the unstable. But when you have this ruthenium-2, it's relatively stable. And then we checked their electrocatalytic property, and then we found that, again, I'm saying that this is the 4,5 redox couple is responsible for water oxidation. And we calculate this over potential. So it is coming at 0.24 volt now. So like if you look at this graph, so now we have reduced this potential approx 300 millivolt with this catalyst. And now we have, like, as you can see, it's much lower over potential of the system. So what it is saying is that if you have the more of the sigma donating anionic ligand, you will be able to reduce the over potential of the system. So that is very good. But the problem comes. So we check that the turnover frequency is very, very low. So it is almost useless, right? So we managed to reduce the over potential, but we are sacrificing something else. So we thought that we want to have the catalyst with high turnover frequency. So can we do that? We thought, okay, let's try. So I have synthesized this molecule called this ruthenium-2 and 2-bipyridine ligand, and then this pyridine carboxylate. So this is 6 coordinated octahedral geometry of this ruthenium compound. And as you can see, so this is the orbital splitting pattern. And from here, you can see that it is a diamagnetic molecule because you don't have any unpaired electron present into the system, and that you can characterize by NMR. That is the technique to characterize this catalyst. And then if you oxidize this ruthenium-2 by 1 electron, you can generate this ruthenium-3 and isolate. And further 1 electron oxidation can give you this ruthenium-4 compound. So if you like look at this, the ruthenium-4 compound, so it has the 7 coordination. So basically it is forming this pentagonal bipyramidal geometry. So normally not all molecule can show this 7 coordination property. So the reason this molecule is showing this, like the 7 coordination space, is because so like now it has forming, as I mentioned, this pentagonal bipyramidal geometry. And if we do this orbital splitting, now we don't have any unpaired electron, and that is why this is showing again the diamagnetic NMR. But you see that like by visually, like let's say that all this ligand environment and everything for this ruthenium-2 and ruthenium-4 are exactly the same. But due to this different oxidation state, their property has been drastically changed. And that is very obvious that when we have this ruthenium-4, the NMR is significantly different than this ruthenium-2. But like, as I mentioned, that to have this water oxidation property, we need to have this water molecule connection to the system. But that is not present in the system. And then we thought, okay, so this was a useless one. But it turned out that it is not. So here I'm saying this DPV. So that is the complementary experiment to the cyclic voltammetry. So here also you are measuring the current by changing the potential. So we had this molecule, and what we found that if we apply the potential here for a while, and then you can do this DPV again, and you can see a huge increase of this anodic current, and that current is responsible for doing this water oxidation. And then we figure it out that so when we are applying the potential at 1.54 here, so basically when we have this ruthenium-4, the ruthenium-4 compound, all of this bipyridine ligand is going out, and then the water is coming because all this chemistry is happening in water. And then forming this compound, active species A, that I already showed you, that one, that it's lower the over potential, but the turnover frequency was very low. And then another species is this active compound is B. So in that case, one of these carboxylates become decoordinated, and then the water molecule that coordinate, and that at high oxidation state, this water molecule form this oxo compound actually. And then we measured the kinetics. So this is the CV, and we found that now the turnover frequency become like, 4 orders of magnitude higher than the previous compound I have shown. So this is a huge improvement in terms of the activity. And then we thought like, okay, why this is showing such a good activity? And then we found that once we have, so here I'm showing just the schematic, the coordination sphere of that molecule. So let's say here I have this ruthenium-5 oxo compound, and one of the carboxylate that is dangling. So when it is dangling, what it is doing this hydrogen bonding interaction with this water molecule. And then it helps, due to this hydrogen bonding interaction, the much of the water molecule is coming closer to that carboxylate, and ultimately it is coming closer to this metal oxo group. And when it is coming closer, then it will form this water nucleophilic attack, and then helps to form this oxygen-oxygen bond. And that was the reason that it was showing such a high turnover frequency. So like this was the platform I was showing, but our newly developed catalyst is showing this turnover frequency here, so which is almost or like among the best one. So it is not the super best, but it's among the best ones. So, and then I'll move on to this heterogeneous catalyst. So now we see that, okay, in this platform, we have this best catalyst is this complex 14, and that has been developed from our group. And so as I was saying, that our demand or our desire is to design a water splitting device. It's not like a like homogeneous molecular catalyst. And this water splitting catalyst device, but always we are having this target to achieve this current density above 10 milliamp per centimeter squared. So can we do that? We thought like, okay, so this molecular catalyst is the very good one. It's showing very good catalytic activity with the turnover frequency above 8,000 per second. So this is the fastest molecular catalyst so far reported in the literature now. So then like they thought like, okay, we want to immobilize that molecule into the surface in order to design the water splitting device. And then they anchored that one, and then they found that they are getting the current density of less than 1 milliamp over the more than 2 hours. But again, I was saying that our demand is to increase this current density above 10 milliamp per centimeter square. Then I thought like, okay, so can we do that one? And if we can, then how we can? So we thought of designing this coordination polymer. So if we are making a coordination polymer, then we can incorporate more than one active center into that system. So with that purpose in mind, we design a coordination polymer, taking this ruthenium TDA, terpyridine dicarboxylate, the ligand framework that is known for like doing this best catalysis, but changing this axial ligand to some kind of bridging ligand and then try to make the polymer. And that is what actually basically I did. So I started with this precursor compound and used this 4,4 prime bipyridine ligand, reflux that one in the alcoholic solvent, and then I got some polymer. I'm calling that one polymer. So with that reaction mixture, what I got, here I'm saying here, that I got like 5 different kind of compounds. So one is this monomer. So where we are having only one ruthenium unit. We found that there is dimer where 2 ruthenium unit is there, and then the tetramer, pentamer, and then the polymer we are calling here up to like more than 10. So it's really like literally it should be the oligomer, but in the coordination chemistry we are calling this one as a polymer. And how I can identify and characterize those molecules. So now here I'm showing this is the NMR of this mononuclear compound. So now you can see that like these two signals are related to this terminal bipyridine ligand. So once you move from mononuclear to dinuclear, you will have one of these as a bridging bipyridine ligand, right? So in the dinuclear compound, you have 2 different kind of bipyridine ligand because the other will be like identical almost. And when we have this bridging bipyridine ligand, we found that it has a signal is lower ppm value than the terminal one. And then we check, and now we can see that the relative integration of these signals are increasing with respect to this terminal bipyridine. So based on the integration relative to this terminal one, we figure it out that we are making a oligomeric compound. The maximum unit we are getting is 15. And of course, like we got this 4 and 5 unit as well. And we have like, and also with this other analytical technique, we characterize all those molecules. So that is very good. And then so our purpose was to design this anode material, right? So we want to put those on the surface. So how we can do that one? So first we thought like, okay, so we want to put those molecule into some solid surface. So one of the solid surface that what we are using is the carbon nanotube. I showed in the introduction that people have tried to that one for the piper stacking. So what I took a little bit of this polymeric compound and I put into a suspension of this multi-wall carbon nanotube. So this is the structure of this multi-wall carbon nanotube. So once I mix them, what I saw is that immediate disappearance of the color when we're mixing here. What it is indicating that all this red color compound is anchored onto this multi-wall carbon nanotube surface, and then the amount of this carbon nanotube is way much higher than the catalyst, and that is why it is not visible. So it means this all the soluble polymeric compounds get stuck into this carbon-based material, and here like I'm showing in that way, it's looking like that. So we thought like, okay, so we did it, but whether we did or not, we wanted to characterize that material, right? So then we did this STM, this scanning tunneling microscope. So it is a very advanced technique to see this molecule into a molecular level by microscope. So we thought like we have this polymer. So here I'm showing this part is zooming portion. So you can see that there is a bright bulbs, right? So this bright bulbs corresponds to this 1 ruthenium unit molecule. And now if you can see the distance between these two bulbs is coming, let's say, is 10.9 angstrom that has been measured from this spectroscopy. So here I'm just showing. And parallel to that, you are seeing that another set of the bulbs, let's say. So this is basically another set of the polymer. So the polymers, they are arranging in this, like in that system in such a way that they are parallel to each other. So that is very good. So that is the first time that we are, by this microscopic image, we are able to see this molecular catalyst onto the surface. And then we thought to do this modeling to understand that, okay, so we saw that they are perfectly aligned by the mixture, like by this STM image. And then we were curious that how they are and how and what kind of things are happening so that they are staying that way. So we decided to do this like the modeling experiment. So basically the DFT calculations we did, and based on this DFT calculation, what we found is that the distance between two ruthenium units is 11.1 angstrom. But with this experiment, like with the STM, we found that's 10.9 angstrom. So it's a very close value, and it is supporting our it is supporting this DFT is also supporting that experimental value, and experiment is also supporting that what the theory we are getting is not wrong. And if we look at a one particular molecule, so it is basically, you see in the bottom is basically the carbon material, and on the top we are saying this wheel-based one is actually the polymer. So in the side view, I'm having like a bit zoom version here. So this is the carbon-based material, and now here we have that one unit of this, let's say one particular unit of that molecule. And what we found that like, so all these molecules are having this CH bond. You see? So the white color I'm showing is the CH bond. So now we found that like the distance between this CH bond and then this carbon-based material is in between 2.7 to 2.8. So this distance is basically not directly a covalent bond, but also it is not a discrete to separate molecule, because if it is a discrete like two separate molecule, then the distance should not be that much low. So it has to be higher. And then we see this one from the front side. And then what we found that each of these units are having such a low distance with the 4 different kind of CH bond. And then we thought like, okay, so there must be something is happening with this 4 CH bond with the surface per each unit of this ruthenium center. And just like if we just rotate it, then we can see this white is showing this actually the hydrogen bond. And then this, the let's say the benzene ring, whatever is showing is basically the graphitic material. So we did this calculation, and what we found is that, let's say if we have this Ru1 is, let's say the mononuclear compound, and we found that because of this 4 CH bond interaction, the enthalpic energy is negative. That is the favorable process, but it has this entropy value which is positive. So if we have a molecule, this entropy value is 20 kcal per mole. So if we do this delta G value, it is coming positive 2 kcal per mole. And we know that any process can be like downhill or easy if we have this delta G value, the negative. So when we have one molecule of water, it is not favorable. So it means like if you are trying to put a mononuclear compound into a graphite surface, then it will not stay. But what we found that if we increase the size, so let's say if you have this pentamer, then in that case, in each unit is having 4 CH bond, and that 4 CH bond is giving 80 kcal per mole binding and the enthalpy of energy, and that is negative, so that is favorable. But if you are having this pentamer, that is still a molecule, right? So it's a one molecule, so it will have the same, almost the same entropy effect. So now, like if you couple them, then you can get this delta G value, as you can see here, is minus 70 kcal per mole. So it is saying that now with mononuclear, it was not going to stay. But if you have like 5 unit, then the energy is suggesting that this 5 unit molecule can stay with each other. And if you increase this unit even much longer, like 10 or 15 units, now you can see that like this delta G value is increased, like it's getting more and more negative, is suggesting that the system is becoming more and more and more stable. So this, so like, yeah, exactly. So this experiment, so this DFT calculation data is suggesting that we are having actually So the CH bond of that molecule is having the interaction with this pi system, and that pi system has been theoretically described as a CH pi interaction. And this is the first experiment. We have some experimental evidence to support that, yeah, we are forming this CH pi interaction. But what I mean to say that is the first molecular catalyst where we are really showing that we are having this CH pi interaction. And that is, I would say, is one of the breakthrough in our field of showing such a nice like interaction and such a stable system. So that's good. So we got that one. So we got the molecular system. We can immobilize into the solid surface. And now we found that, okay, so the system is forming thermodynamically very favorable. So it is going to be a more stable. So that's perfectly fine. But that was not our main goal, right? So we wanted to design the molecular anode. So in order to do this water oxidation, so then we need to put those material what we got that one into a conductive surface called glassy carbon disk electrode to do this electrochemistry. So we are putting that one. So here I'm just showing this representative example. So we have this glassy carbon electrode, that is the conductive material, and we are putting this molecular anode material what we are getting from this mixture. So we got this one. We take again this cyclic voltammetry because as I mentioned that is the technique we're using. So now we see like the two redox couple. So this is ruthenium 223 and this is 324 redox couple for this compound, and is known because its mononuclear unit has been already published and known. And then redox potential are perfectly matching with this system. And then we knew that this is not the real catalyst. So yeah, the real catalyst is that you need to apply the potential here, and then you will form completely new compound. And that is actually the active catalyst. And that is what exactly we found here. So we apply the potential here. And now we see that we are forming some new compound upon applying the potential here. And then we are doing the cyclic voltammetry. And now we are seeing the current density in the scale of like almost 240 milliamp per centimeter square. So I would say that our scientific community, this is the first time where with the molecular catalyst, you are getting the current density like that is above, let's say 10 milliamp. So so far before it was like a maximum the 10 milliamp, but now we got the huge improvement in this current. And then we are trying, if you look into the close view, so the black one is our starting material, right? So the starting material is nothing but the 7 coordinated compound without coordination of water. But the red is showing that now we have this coordination of water at high valent oxidation state. This water is forming like ruthenium water compound is actually forming ruthenium oxo. And now like these two redox couple is related to this ruthenium 223 and 324 redox couple. And these are the pH dependent, which is suggesting that your metal is coordinated with the water, and depending on the pH, your water can be protonated or deprotonated. So that is a very strong evidence that we are having this catalyst. And then like if we compare our system, like we have this mononuclear compound, we thought like we prepared that one for making this molecular anode through this through this pi-pi interaction. And now if we compare the value under identical condition, I would say, now we have seen the current density improvement happen like almost 2 orders of magnitude. So that is also like another breakthrough in our molecular water oxidation field. And then we thought like, okay, to check the stability, because at the end, ultimately, we want to do this bulk electrolysis to continuously oxidize water molecule in order to get the oxygen and then hydrogen. So we take that and we got that like the current density of what we are getting in this technique is approximately like 31 milliamp, and it's remained stable over more than 12 hours. And then before I start and after I stop, I was checking the cyclic voltammetry in order to check the stability and the molecular integrity of these systems. So now you will see that we are almost saying the similar current, and now you can see that internal part that the molecular integrity remain intact into the system. So now I'm saying so what I got from this system is that the current density now we are getting 31 milliamp, and then the turnover frequency is like 8,000 per second, and its turnover number is like 3 lakh. But so one thing is here what I wanted to say is that as I mentioned in the introduction, that our goal was that the J current density has to be above 10 milliamp. And now we got a perfect system that shows even much higher, so 3 times higher than the requirement of this current density. So it was, as I was saying, that it was a great breakthrough in our field, and that is why like it published in a very good journal called Nature Chemistry. So that is one of the like prominent journal in our scientific community. So yeah, that was my PhD work. I was just I present, and then like I moved to US for doing my postdoc, and then here I started working with oxidation of molecular, like oxidation of organic compound, basically. So in my PhD, I was doing oxidation of water to oxygen electrochemically, but in my postdoc, I thought to use this electricity and do this transformation of organic molecule, and why? So let's consider the one simple transformation of oxidation of alcohol to a carboxylic acid. So whatever the known method is known in the literature is using the transition metal catalyst. For example, this KMnO4 or ruthenium oxide or the bleach or other chromium oxide based reagents. So those chemical, like when you are using, so you are getting this, you are doing this transformation of alcohol to carboxylic acid together with, you are generating a very toxic chemical as a byproduct in that system, which is not environmentally friendly, right? So we thought that whether we can remove the use of any chemical reagent with the electricity, because let's say if you are using this electrochemical reaction, so then your oxidant or reductant is only the electrons, and that you are getting from the electricity, right? So then you don't have to use any chemical. So you just like need to switch on your power button to do this oxidation chemistry, and that is happening by electrons and nothing else. So then it avoid of using any kind of hazard or oxidant to use this one. So it is becoming basically a very green chemistry. And also, if you can think of doing this reaction in water, then you are done, because all this natural process is happening, let's say, at the neutral pH. So if you like remove this, any kind of the oxidant, this chemical oxidant, and if you can do this reaction in water, then you are solving a lot of problem. And also like the electrochemistry has that benefit that you can control the potential, whatever you want. But each of these chemical, they have their fixed oxidation potential, so that you cannot change it. But the electrochemically, you can change the electrode potential, and whatever potential you want and you need, you can manipulate that one. So it's relatively way much easier to control that one. But of course, like it has a complication in some other aspect. So here I'm showing one molecule. So that is a drug molecule called levetiracetam. So that is basically used for the medication for this epilepsy disease. So that disease is basically the chronic disorder of the brain. So if someone is having, then they are taking this one as a medicine to cure that, to cure that problem. So like to synthesize that molecule, so it has like a few steps. So starting from, let's say, the lactam and amine, you can get this alcohol. And then you need to oxidize this alcohol to a carboxylic acid. And now this carboxylic acid, once you have this carboxylic acid, then you can easily replace this hydroxide with amine to get this final product. So to design this, or like to synthesize this drug molecule, so the main important reaction was the oxidation of alcohol to a carboxylic acid. And as you can see that it has a chiral center. So you want to get this molecule with optically pure as possible. So, okay, so then we thought like of doing this transformation, but the problem what we encountered, that we want to oxidize this alcohol to a carboxylic acid, but it has to go through this aldehyde. And once we have this aldehyde, it can epimerize, because in presence of water, this can like do the hydrate and then form this diol. And when this diol compound will be back, then it will change the stereochemistry. And if the stereochemistry is changing, then it will have no use for the medical purpose. So we want to do this transformation efficiently, but we need to keep in mind that we want to keep this stereocenter as intact as possible. So to do so, like we design like two different kind of set of experiment electrochemically. One is batch batch reactor. So this is basically you are taking a beaker, you are adding all the reagent what you need, and you are putting these two electrode, and you are connecting this electrode to the power supplier, and you are switching the power, and you are doing that chemistry, and you are getting the product. So that is in the batch. But in case of the flow, now you have the electrode material outside of this vessel. So you have this solution into this vessel, so where you have your reagent, and you are flowing those solution by flow to this electrode material, and then the reaction is happening at the electrode, and then you are collecting back into the system. So that is called this flow, flow setup. So the batch cell and then the flow cell. And here I'm showing this is the reaction what I was targeting, like starting from this alcohol to get this carboxylic acid. And the panel A is showing the cyclic voltammetry. So the cyclic, as I said before, the cyclic voltammetry can tell you about this kinetics and all other parameters, like all other factors. So the blue one is showing this, the cyclic voltammetry we are carrying out in the batch under exactly identical condition. But so the red one is showing that when we are doing in the flow, and that is like in undivided flow. So what does it mean? That in case, like in this flow cell, we have this cathode and anode. And in between, if there is no separation, then we call that one undivided flow cell. But if we are putting some divider, some membrane, then it is a divided cell. So in case of the undivided cell, we got this, that the red trace is showing that one. But the black one is showing that when we have this divided cell, then even we are improving the kinetics and we are getting this faster reaction. And that is already reflected when we are calculating the yield. So for example, so we are applying the potential of the current here, and then we wanted to see that the formation of the product. And what we found, like I'm showing in the panel B, is the yield versus time. So in case of the batch, so to do this transformation for a particular scale, it is taking, let's say, more than 11 hours. But when we are doing the same reaction in the divided cell, it is finishing less than 30 minutes. So it's like we have developed so in the flow process, it is so efficient. And now, let's say in the industry, they take care of like how much product you are forming by time. So that is called the throughput. So here we are plotting this throughput. So gram per hour in the panel C. And in case of the batch, this throughput is coming that 0.06 gram per hour. But when you are doing the same chemistry into the flow, in divided flow, so now you have improved this activity like in 50 times higher than that one. And also, like I was saying, that we must need to consider about the stereochemistry, and then the black one I'm showing in the divided cells. So we can see that the pH in between 8 to 9, we can have this stereochemistry remain intact, which was not in the case of, let's say, the batch cell or in the undivided cell. So we found, and then we developed a very efficient method for making the chiral carboxylic acid. And then like in the industry, they think of making this one scale up and for selling that compound, right? So like all this chemistry here, I'm saying this, the flow cell, which is small in size here. But if you want to do this scale up, just you need to increase the size of your reactor. And that is what exactly we did. And then we have synthesized like 200 grams scale of this molecule with 91% yield and having the like E retention above 97%. So it was, so this is the work of my postdocs. I'm presenting partially. So so like now I move to this conclusion and it will be okay. So I showed you that like geometry and then ring size can have a dramatic effect on the turnover frequency, that is the activity of the small like catalyst. And I showed that like introducing the sigma donating anionic ligand can help to reduce the over potential of the system. And then I showed another example that where you can form this 7 coordinated compound, this pentagonal bipyramidal geometry, and that ultimately can generate this active catalyst with very high turnover frequency. And here I'm saying that like the 1D polymer, the coordination polymer, that is the most like important part of my thesis, is that I'm showing like a very high current density in the CV and also is very, very stable for over a long period of time. And just we are comparing that one that we can see if we can do this head-by-head comparison, it's a huge improvement. And in my postdoc, so I used this electrochemical technique but I wanted to transfer that knowledge into a, let's say, the medicinal chemistry or in the process chemistry, and that is what we did of making this drug molecule. And then, yeah, so at the end, I would like to thank my PhD supervisor, where I have spent so far my most of the time research work. So here is my Professor Anthony Lobet, and this is my group. If you can see me here, I am, my eyes are closing. And in 2018, I moved to this MIT. So this is the group. He's the Professor Sunath Yogesh, and these are my colleagues. And this is where I am right now in UW Medicine. So he is the Professor Shannon Stahl, and this is our group. So we took this picture just few days back. And of course, like those kind of work is impossible if we don't get the funding. So these are the funding source. I would like to thank to them. And then the most thank can go to this Department of Chemistry, Maulana Azad College. So this is the picture I found. So here, like not all the stats and my friends are present here, but I would like to thank very, very much, because so like whatever I am now today is because like I build up the foundation of my chemistry after entering into this college. So this is the thankless job, I would say. So I'm very proud to be a part of Maulana Azad College. So here is the photo of when I was there. So my friends, here I am now. So not everyone is here. I could not find the picture of all. And this is the picture I'm showing, like from the IIT Bombay, and they are my classmates, batchmates. So I would like to thank everyone because of the friends, family, and the help of guidance from teachers and everyone helped me to be what I am here today. So thank you very much for your attention. I'll be happy to have any questions.
Thank you, Dr. Hawk, for your excellent presentation. Now this is open for discussion. We have a few questions in our chat box. Mondol. The question is how turnover frequency related to catalytic efficiency, and what's the role of concentration here? I repeat, how turnover...
Okay, that is a very good question. So there are different way of like benchmarking the catalyst, right? So like how you want to say that your catalyst is good or bad. So let's say if you are doing like any kind of organic synthesis, then the catalyst is coming like you are using 5 mole percent, 10 mole percent, 15 mole percent. So the turnover, like let's say if you are using this 5 mole percent of the catalyst, then the maximum turnover you can get is 20, let's say. And then if you are getting that one, but you want to, so you are not thinking about only the product yield, but you are also thinking about the time, right? So how fast, so that like yield you are getting in, let's say in 1 hour or in 1 minute. So that is how you are defining your catalytic activity. And to define this catalytic activity, this is the turnover frequency is defining as, let's say, how many moles of product you are getting when you are using 1 molecule of catalyst in 1 second. So that is how it's very important. And it is nothing to do with the concentration, because when you want to like increase the higher concentration, basically you are increasing the amount of the catalyst. And then if you increase this high amount of the catalyst, then basically you are having this lower turnover number. So let's say instead of using this 5 mole percent, if you are using like 50 mole percent, then you will get the turnover number 2. And then if you are getting this turnover 2 in 1 minute, then you are getting this turnover frequencies 2. But if you are getting the same thing with 5 mole percent, then your turnover frequency is going to be 20, right? So it is not directly related to the concentration. So if you are increasing the, so it can affect, but the turnover frequency will not matter at all. Like if you wanted to benchmark with the turnover frequency.
Thank you, Dr. Hawk. Before going to the next question, one important announcement. Feedback link has been given in the chat box. Participants, those who are not registered, please fill up the form with, and those who have registered, feedback link has already been sent through the mail. So they can fill it up later within midnight today. It is important for only not registered participants. Thank you. Our next question is, it is a very good question. how artificial photosynthesis benefit the society or future.
Okay. Oh, yeah. How artificial photosynthesis benefit the society or future generation? Wow. So that is a wonderful question. Yeah. So that is what our dream is, right? So yeah, that is what we wanted to do. So then imagine that, like, okay, the ideal world, how and in which way we are thinking. So now we are like, let's say, the car and bus, we need this petrol and diesel. So those are coming the fuel, and that is coming from, let's say, the fossil fuel. But imagine that if we are generating a photosynthetic device, if we are getting a catalyst that can do this water oxidation, so that basically generate the oxygen, so that we don't care, but what we care about the product, like hydrogen. So the hydrogen is the source of fuel. So imagine that you are taking a bike and you put like 1 liter of water, which you don't have to buy. So you have such a catalyst. That catalyst will doing this oxidation of water. You are generating this hydrogen, and you are running that car by hydrogen, right? So that is the dream. Like, that is what we wanted to achieve in future, that we wanted to replace all the fossil fuel just by using the water. So we wanted to take the advantage of the natural source of water to do that chemistry, like do that purpose. So I'm hoping that our future generation, or probably we, when we'll be older, probably able to see the benefit of that one.
One more question from Dipanjan Ghosh. Can artificial iron complex be used as it is in the same group of ruthenium?
Yes, that is wonderful questions. I really like that one. Yeah. So like, let's say, yeah, that is what, like, let's say the ruthenium is way much expensive than than the iron, because the iron you can get everywhere, anywhere, and it's very cheap. So if we can make a catalyst based on the iron, then that would be the ideal one. So then you don't have to pay much money. But the main problem with this, the first transition metal complex, is that you are actually forming the complex, and then you want to do this water oxidation in water, right? Because you need to have water present in the system. Then there is a significant ligand exchange between water and whatever the ligand you are putting. So once you have, let's say, when you put the ligand, and in presence of water, that ligand can replace with water, and then you are forming ultimately this metal aqua compound, iron aqua compound. And when you are applying the potential, you are ending up with making this iron oxide. And when you have this ending with the iron oxide, then you don't know actually what you are getting. Probably you are getting the water oxidation, but you don't know what you are getting and how much you are getting. And then when you have this metal oxide, then you are limited with the turnover frequency. Then you cannot improve it. But still, there are reports, and people are trying to do this molecular water oxidation catalyst to the faster transition metal. So we have a bit success with the copper, and with the iron, we have this problem of the stability issue when we are trying to design a molecular catalyst in presence of water.
One last question. Why the naturally occurring WOC, which you mentioned in the beginning, is not used? Is it due to synthesis or separation reason?
Oh, yeah, wonderful. That is very interesting questions. So in the nature, like, that is what we showed, that the chemical structure of this catalyst. But I in the introduction, I mentioned that it is not only about the catalytic metal center. It also has a great impact on the secondary coordination sphere. So in the natural photosystem too, so next to this manganese metal clusters, we have this tyrosine. So that is another like a ligand. So that helps to do this. So like tyrosine, and there are many molecules. So there are a bunch of protein molecules around this metal center, and that is helping to achieve this high turnover frequency into that system. So the scientists, they have tried to design those catalysts, but we could not get success to get this such a turnover frequency, because we are not able to exactly mimic the environment what nature is doing. So that is why we are not able to reach that much high turnover frequency, but we wanted to achieve, right? So then we try to find some alternation that, okay, so the first trial was that one. So use this manganese catalyst and then try to develop the method. And then we got stuck that we are making the compound, but we are not getting the activity because we don't have this secondary sphere. So that was the reason that people tried to make this artificially. Some like ruthenium based or iron or this copper based catalyst were putting this different kind of ligand environment to this complex to get this activity.
One more question. Can we, from Ronit Malakar, can we replace bipyridine ligand by a sigma donating anionic ligand as it will increase
the activity
of the catalyst?
Oh, yes. So yeah, that is what we can do. Right. So one of the example where I showed that we have this 2 sigma donating ligand, right? So let's say if you are thinking of putting 3 to sigma donating ligand, then you will be able to reduce another 2 to 300 millivolt potential. And in that case, like you will have this catalyst, which will have this potential below than the thermodynamic potential, right? So if you are having this ruthenium 4,5, this high valent metal oxide below than the thermodynamic potential, then that is not going to work. So that is one problem. And also like the catalytic activity, it depends a lot, right? So with the sigma donating ligand, we are able to reduce this over potential, but we really cannot say that it can improve the turnover frequency. Again, it depends on the type of ligand what you are using.
Last question from Abdul Aziz.
Yeah.
How can we transform linear 1D polymer into 2D organic covalent?
Oh, that is wonderful. So we did that work, but it was unpublished. That is why I didn't present. So imagine that you have this linear bipyridine ligand, right? The 4,4 bipyridine. So that is a linear molecule, and that is why it is giving the 1D polymer. But let's say, imagine that if you are using another kind of molecule, for example, let's say in the middle you have the benzene ring, and then like let's say in 1, 3, and 5 position you have pyridine connection, like pyridine connection, and then now you have this pyridine, right? And then you can have this catalyst like this molecular unit, and that you can connect with this pyridine and then pyridine. So you have in the center that is one molecule, and that can like form this 3D network. And even like if you can choose this bridging ligand in such a way that you can form this 2D polymer as well, and you can make 3D polymer as well. So it's just like we need to change this ligand environment. So that work is like, yeah, it's partially done, that work. So yeah, thank you very much for this questions.
Thank you. If anyone from faculty member want to ask any question.
May I ask any question to Azmaul?
Yeah, sir. Oh.
Hello, Azmaul. Can you hear me?
Yes, Sundabachi, sir. Yeah, sure. How are you?
Sure. I am really feeling proud to get you, my student.
Thank you.
And really impressed
You.
your talk, your thinking representation. My question is regarding your molecular oxygen device. You have used most probably cathode as graphite cathode. Is that it?
Yeah, it depends, not really, and depends like what we wanted to do in the cathode material. So let's say like so far, like for example, like from the water we are generating the proton. So if we wanted to reduce the proton, the so far best catalyst is based on the platinum metal. So then we are using this platinum based material for as a cathode material for doing that one. But if we wanted to think about the economic way, then the platinum is way much more expensive than the graphite electrode. And then with the graphite electrode, the main problem we are having is that the graphite electrode is doing a much higher over potential than the platinum electrode. So then we need to compromise, right? So in one thing that we need to put like high electricity, if we are using this graphite, and if we are thinking of using this platinum, then we are investing more money on the platinum electrode. So then we need to compromise in between these two. And then when one is leading, we go with that one.
No, no. My question is, what happens if we use 3D graphene type of compound here instead of using graphite?
Okay.
Particularly graphene, that type of CH pi interaction is more prominent,
Yes.
much more probability for stacking your catalyst to particularly in cathode graphene cathode.
Yes.
Have you performed any experiment using 3D graphene?
Exactly. Yes. So yeah, I didn't show it here. So we did like another project. So where basically we are taking this carbon ink. So
Yeah.
that is like so that is not a graphite. So that is a carbon ink, and it is like way much porous. And then we are incorporating this molecular catalyst into that system, and then we are mixing, and then we are making the ink. And then that one we are printing on a paper. That paper is a conductor, the polymeric paper, and we are putting that molecule inside that one. So the whole integration, so this carbon material molecule and then the electrode is the integrated part of the anode. So we didn't try, so we tried with the carbon paper. We tried with this yeah, I showed you the multi-wall carbon nanotube, but I think we didn't try with that one what you mentioned. But I am hoping that that will also give like even much better CH pi interaction, right? Because that will be even much more 3D structure.
Yeah. Have you any plan to in your near future to generate this type of battery? That means particularly
yes.
if it is possible to recycling the entire process.
Yeah, that is what. So okay, so yeah, that is the dream, right? So we want to do that one. So yeah, that like we have done into the research lab, but we wanted to apply that one in a real practical application if we can. So the thing is like, yeah, so the thing is like there are several steps to reach there. So we, the molecular chemist, we are thinking about the very, very basic chemistry aspect of developing that one. And then we need some engineering aspect as well, like when we wanted to do this scale up or let's say the battery designing and all. And like each and every step we need the optimization, so it is a time taking process. So definitely like yeah, let's say in my like now I'm doing the postdoctoral research in one particular group, but at some point I believe and I want to be a faculty, and then I wanted to have a research group where one of my topic will be this one. So we wanted to make this one economically feasible and have to have a practical application.
My blessing and wish always for you.
Thank you, sir.
Thank you, Asmaul.
Thank you, everyone. Now the question answer session is over. Now I over to Professor Ajanta Mukherjee for the next part of this webinar.
Yes, thank you. We have almost reached the concluding part of our webinar. But first and foremost, I would like to say that we are completely blown away by the sheer brilliance of your lecture, Dr. Hawk. And it was so fascinating to hear about your journey from Antardip till Wisconsin, Madison,
Yeah.
Antardip. And it really underscores the fact that talent and hard work can take anyone anywhere, and sky is definitely not the limit. And I would really like to thank and commend the speaker on his ability to explain complex systems in very simple language, which is evident by the fact the number of questions put forward by the students. And it really seems that you have really stimulated their curiosity, which was the objective of our webinar. And in his talk, he has highlighted the need for renewable source of energy and beautifully explained natural photosynthesis, artificial photosynthesis, development of artificial complexes or coordination compounds, their advantage over the metal oxides, and development of linkages to anchor the catalyst, covalent, non-covalent linkages, and his talk truly explained everything in vivid detail. And it most importantly, it involves green chemistry, which is really the need of the hour, considering the climate crisis which we are facing right now. So it was truly an enriching experience, and I'm sure every participant has enjoyed today's session. So now we have come to the concluding part, and I must formally present the vote of thanks. So first and foremost, I would like to thank the speaker of the webinar for accepting our invitation at the very first proposal. And I would like to thank the respected principal of our college for his kind patronage for such programs of excellence. I would like to thank the respected coordinator of IQSE for always inspiring the faculty members to strive for newer and innovative endeavors. I would like to thank the respected head of the Department of Chemistry for his initiatives and support always to motivate both the students and faculty members and take the department to new heights. I would like to thank the organizing committee comprising Dr. Shubhadeep Shamanto, Dr. Orijit Kundu, Dr. Shonju Dash, and all other faculty members of the department for their cooperation and support. And last but not the least, I would like to thank all the participants of this webinar. Especially, I would like to thank all the teachers of Dr. Asmaul Haq who have been able to attend this webinar. And it must have been really a very nostalgic moment. And all the students, and I hope they have been inspired and motivated by today's talk. And we hope to conduct more such lectures in the upcoming days. And I also wish Dr. Asmaul Haq all the very best for his research innovations. And we hope that his research really goes on to reach the extreme heights. Thank you. Thank you all.
Thank you very much. Thanks a lot, everyone.
Thank you, Dr. Asmaul.
Thank you.
Thank you, Dr. Asmaul Haq.
Thank you, sir. Thanks a lot.
Thank you, Dr. Haq.
Thank you.
Thank you, sir.